Hello students, I welcome all of you for today's first chapter discussion in class 8 mathematics. In the earlier classes, you have already seen about different numbers like natural numbers, whole numbers, integers. Before proceeding further, let me ask you some questions. First question is, between 2 and 3, how many integers are there? Yes, the answer is no integers exist between 2 and 3. Second question, after 3, what is the next integer? Good, it is 4. Third question is, what is the solution of the equation 2x minus 1 is equal to 0 in integers? Yes, we cannot find any solution for this equation in integers, as the solution of this equation is x is equal to 1 by 2, which is not an integer. Now, we are entering into a new system of numbers where we will get the answers for all these questions. So, such type of numbers we are calling it as rational numbers. Now, let us see what is the definition of rational number. A rational number is a number of the form p by q, where p and q are integers and q is not equal to 0. Note that to construct these rational numbers, we are using integers. Suppose if a is any integer, then we can write this a as a divided by 1, and so that a is in the form of p by q. This says that every integer is a rational number. However, all rational numbers are need not integers. For example, 1 by 2, it is not an integer, but it is a rational number which acts as a solution for our previous question. So, by using integers, we are constructing this new number system which we call it as rational numbers. Now, let us observe some very interesting properties of rational numbers. In fact, you have already seen we can add any two integers. In fact, we can add any two natural numbers also. Now, let us see such type of addition, whether is it possible for rationals or not. Let us consider some examples. First example is minus 3 by 8 plus minus 4 by 5, which is equal to, you know how to add these two numbers, the answer is minus 47 by 40, which is a rational number. Second example is 4 by 7 plus 6 by 11 is equal to 86 by 77, which is also a rational number. Thus, when we add any two rational numbers, then the addition of those two numbers is also gives a rational number. We call this as closure law, that is, our rational number set is closed under addition operation. Let us define what is this closure law as a definition. Closure law: for any two rational numbers a and b, the number a plus b is also a rational number. Interestingly, not only for addition, you can see that subtraction, multiplication are also closed under rational numbers. You can find different examples with these two operations. Now, the question is whether division is closed under rational numbers or not. Let us take two rational numbers, say 2 by 3 and 7 by 5. If you take 2 by 3 divided by 7 by 5, you know how to divide these two numbers. In that case, the operation becomes 2 by 3 into 5 by 7, that is equal to 10 by 21, which is again a rational number. Hold on, you can see that division is closed under rationals, but unfortunately, if you consider 0, then for any rational number a, divided by 0 is not possible. So, that is why with respect to 0, the division operation is not closed. Even for one element, if the operation is not closed, then we say that it is not a operation with respect to that all. Therefore, division is not closed under rational numbers. That means, the division of non-zero rational numbers is actually closed. Now, let us consider the following table. Let us fill it by using cross mark or right mark. Right mark indicates the operation is closed, cross mark indicates the operation is not closed. Let us observe the following table with respect to all numbers and with respect to all the operations. It is given as follows. Now, the operations taken in this chart are addition, subtraction, multiplication and division, and sets are rationals, integers, whole numbers, natural numbers. Now, let us observe with respect to rational numbers. Rational numbers under addition, it is closed, therefore, right mark is there. Under subtraction, it is closed, therefore, right mark is there. Under multiplication, it is closed, therefore, right mark is there. As we seen, division is not closed, therefore, cross mark is there. Integers closed under addition, closed under subtraction, closed under multiplication, but not closed under division. Similarly, for whole numbers closed under addition, but there are no negative numbers present in this set, therefore, it is not closed under subtraction. Again, it is closed under multiplication, but not closed under division. For natural numbers, it is closed under addition. Again, because of the not present of negative numbers, it is not closed under subtraction, but closed under multiplication, and again not closed under division. Thus, this entire chart gives the idea about closed operations with respect to rationals, integers, whole numbers and natural numbers. Now, let us observe the second property, we call it as commutative property. You know already how to add two rational numbers. Let us observe the addition of two rational numbers by taking following example. Minus 2 by 3 plus 5 by 7 is equal to, you know how to take the addition of these two things, which is equal to 1 by 21. Now, I am taking 5 by 7 first plus minus 2 by 3. Then also you can see that the operation gives the answer as 1 by 21. Similarly, second example, minus 6 by 5 plus minus 8 by 3, which is equal to minus 58 divided by 15. Similarly, minus 8 by 3 in a reverse way I am taking plus minus 6 by 5, this also gives minus 58 by 15. By observing these examples, you can see that the addition of any two rational numbers in any direction always gives the same answer. This property we call it as commutative property. Let us state this as a definition given by as follows. Commutative law. For any two rational numbers a and b, the addition satisfies commutative law, that is a plus b is equal to b plus a. Note that the same is true for multiplication also. That is, for any two rational numbers a and b, a into b is equal to b into a. Let us observe this by taking one example. 2 by 3 into 5 by 2 is equal to 10 by 6. Similarly, 5 by 2 into 2 by 3 is equal to 10 by 6. In both the way the answer is same, but note that the operation subtraction and division are actually need not be commutative. For example, let us see how they are not commutative in these two examples. 2 by 3 minus 5 by 2 is equal to minus 11 by 6, but 5 by 2 minus 2 by 3 is actually equal to plus 11 by 6. Therefore, minus 11 by 6 is not equal to plus 11 by 6, and so they are not equal. Similarly, for division, 2 by 3 divided by 5 by 2 is equal to you know how to operate the division. 2 by 3 into 2 by 5, that is equal to 4 by 15. But 5 by 2 divided by 2 by 3 is actually equal to 15 by 4, and so they are not equal. Now, let us complete the following table, which contains all 4 basic operations and with respect to different number sets. It is given by as follows. So, the operations given as addition, subtraction, multiplication and division. The number sets are rationals, integers, whole numbers, natural numbers. First, with respect to addition, rationals are commutative, therefore, we have to put yes. With respect to subtraction, rationals are not commutative, therefore, we have to put it as no. With respect to multiplication, it is yes. With respect to division, it is no. Similarly, for integers, with respect to addition, it is commutative, so yes. With respect to subtraction, it is not commutative, so no. Then with respect to multiplication, it is yes, and with respect to division, it is no. Similarly, for whole numbers, for addition yes, for subtraction no, for multiplication yes, for division no. Similarly, for natural numbers, for addition yes, for subtraction no, for multiplication yes, for division no. In this way, this entire chart gives about the information of commutative law under different operations under different number sets. Now, let us see the third property, we call it as associative property. It states that for any 3 rational numbers a, b and c, a plus b plus c is equal to a plus b plus c. Similarly, under multiplication, a into bc is equal to ab into c. This is called associative property. Let us check this with one example. Let us take 3 rational numbers as follows: 3 by 4, 2 by 7 and 1 by 5. For these numbers, first look at for addition. 3 by 4 plus 2 by 7 plus 1 by 5 is equal to 3 by 4 plus that addition gives 17 by 35, then total addition gives 173 by 140. Now, next 3 by 4 plus 2 by 7 plus 1 by 5. The addition of first two numbers gives 29 by 28 plus 1 by 5, then the final answer gives as 173 divided by 140, both are same. So, 3 by 4 plus 2 by 7 plus 1 by 5 is equal to 3 by 4 plus 2 by 7 plus 1 by 5. Similarly, for multiplication, if we take the same numbers, look at what happened. 2 by 3 times 1 by 4 into 5 by 6 is equal to 2 by 3 into 5 by 24, and that is equal to 10 by 72. Now, 2 by 3 into 1 by 4 gives 2 by 12 into 5 by 6 also gives 10 by 72. Hence, 2 by 3 into 1 by 4 into 5 by 6 is equal to 2 by 3 into 1 by 4 into 5 by 6. We can check that this property does not hold true for subtraction and division. Now, the next property is a special element called identity exists in the rational number set. This property we call it as identity property. For any rational number x, there exists a rational number y such that x plus y is equal to y plus x is equal to x. Similarly, for any rational number x, there exists a rational number say z such that x into z, which is equal to z into x, which is equal to x. In case of addition, y is denoting by 0. In case of multiplication, z is denoting by 1. These two numbers are called as identity elements with respect to addition and multiplication respectively. Now, the next property is inverse law. For any rational number x, there exists a rational number y such that x plus y is equal to y plus x is equal to 0. Similarly, for x not equal to 0 is a non-zero rational number, then there exists a rational number z such that x into z is equal to z into x is equal to 1. In case of addition, y is called the additive inverse, which is denoting by y is equal to minus x, and in case of multiplication, z is called the multiplicative inverse and is denoting by z is equal to 1 by x. Note that 1 by x is also called the reciprocal of x. For example, let us take a rational number 3 by 2. Then for 3 by 2, we can take minus 3 by 2 such that 3 by 2 plus minus 3 by 2 is equal to minus 3 by 2 plus 3 by 2 is equal to 0. Therefore, minus 3 by 2 acts as a additive inverse of 3 by 2. Similarly, 3 by 2 into 1 by 3 by 2, which is nothing but 2 by 3 is equal to 1. Therefore, 2 by 3 acts as a multiplicative inverse of 3 by 2. Next, one more property, we call it as distributive property. For any three rational numbers a, b and c, we have a into b plus c is equal to ab plus ac. Also, a plus b into c is equal to ac plus bc. These two properties are called right distributive and left distributive properties for rational numbers. For example, look at for 1 by 2, 1 by 3 and 1 by 5, 1 by 2 into 1 by 3 plus 1 by 5 is equal to 1 by 2 into the addition of those two things gives 5 plus 3 divided by 15. Therefore, the final multiplication is 8 divided by 30, and 1 by 2 into 1 by 3 plus 1 by 2 into 1 by 5 is equal to 1 by 6 plus 1 by 10. This addition is equal to 5 plus 3 by 30, that is also equal to 8 by 30. Therefore, 1 by 2 times 1 by 3 plus 1 by 5 can be written as 1 by 2 into 1 by 3 plus 1 by 2 into 1 by 5. Similarly, we can also see that 1 by 2 plus 1 by 3 times 1 by 5 is equal to 1 by 6, and 1 by 2 into 1 by 5 plus 1 by 3 into 1 by 5 is equal to 1 by 10 plus 1 by 15, that is also equal to 1 by 6. That is 1 by 2 plus 1 by 3 times 1 by 5 is equal to 1 by 2 into 1 by 5 plus 1 by 3 into 1 by 5. These are the very important properties of rational numbers. Let us list out closure law, commutative law, associative law, identity law, inverse law, then distributive law. Now, let us see some very interesting questions and try to answer these questions one by one. First question is, find the rational number that does not have a reciprocal. Answer is 0 is the only number which does not have reciprocal. Second question is, find the rational numbers that are equal to their reciprocals. It's a very interesting question. Let us see the answer. Suppose x is a rational number such that x is equal to its reciprocal 1 by x. So, x is equal to 1 by x implies by cross multiplying x we will get x square is equal to 1, and therefore, x is equal to plus or minus 1. Hence, 1 and minus 1 are the rational numbers that are equal to their reciprocals. Third question, find the rational number that is equal to its negative. It is also very interesting. Let us see the solution. Let x be a rational number such that x is equal to its negative, that is minus x. Then by taking minus x on the left hand side, it becomes x plus x is equal to 0, that is 2x is equal to 0. Since 2 is not equal to 0, the only possibility is x is equal to 0. So, 0 is the only rational number that is equal to its negative. Question number 4, is 8 by 9 is the multiplicative inverse of minus 1 1 by 8. Very interesting. Look at the answer. Look at 8 by 9 into minus 1 1 by 8 is equal to 8 by 9 into minus 9 by 8, that gives minus 1, which is not equal to 1. Therefore, 8 by 9 cannot be the multiplicative inverse of minus 1 1 by 8. Question number 5, is 0.3 the multiplicative inverse of 3 1 by 3. Very interesting. Look at the answer. Look at 0.3 is actually equal to 3 by 10 and 3 1 by 3 is actually equal to 10 by 3. So, 0.3 into 3 1 by 3 are nothing but 3 by 10 into 10 by 3, which is equal to 1. Hence, 0.3 is the multiplicative inverse of 3 1 by 3. These are all some interesting problems given in the textbook. Now, we are going to see one more important section about rational numbers. You know already that between given two integers, there are definite number of integers present. For example, between minus 2 and 2, we can see that minus 1 is there, 0 is there, 1 is there. Similarly, if you try to find the number of integers between 2 and 3, there are no integers present. Now, we are going to see between two rational numbers, how many rational numbers are possible. In fact, we can observe that there are plenty of rational numbers are present between given two rational numbers. So, to find all those rational numbers, let us discuss some interesting methods. First method. Here we observe this method by considering one example. Let us take two rational numbers 1 by 9 and 8 by 9. Then by increasing the numerator by 1, we get after 1 by 9, 2 by 9, 3 by 9, 4 by 9, 5 by 9, 6 by 9 and 7 by 9, such that they are all lie between 1 by 9 and 8 by 9. Also note that 1 by 9 can be written as 10 by 90 and 8 by 9 can be written as 80 by 90. So, starting from 10, increasing the numerator by 1, we get the numbers like 11 by 90, 12 by 90, 13 by 90 dash 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 up to 79 by 90 are all also lies between 1 by 9 and 8 by 9. Note that they are 69 in number. Similarly, by adding zeros to both numerators and denominator, we can expand the possibilities of finding the rational numbers between them. That is, for 1 by 9 is equal to 100 by 900 and 8 by 9 is equal to 800 by 900. Then we have 101 by 900, 102 by 900, 103 by 900 dash 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 up to 799 by 900, which are all 699 numbers and so on. In this way, we can find the rational numbers between any two given rational numbers. Let us discuss about method 2. Here, by finding the mean of given two rational numbers, we can always find a rational number which lies between these two numbers. In your lower level classes, you know already how to find the mean of two numbers. The mean of given two numbers are nothing but their sum divided by 2. Let us observe this by taking one example. Consider two rational numbers, say 1 by 9 and 1 by 6. Then the mean of 1 by 9 and 1 by 6 is 1 by 6 plus 1 by 9 divided by 2. that is 5 by 18 divided by 2, that is nothing but 5 by 36. So, 5 by 36 lies between 1 by 9 and 1 by 6, that is we can find a number between the given two rational numbers. Thus, we see that 1 by 9 is less than 5 by 36 is less than 1 by 6. Similarly, by taking 1 by 9 and 5 by 36 as well as 5 by 36 and 1 by 6, we can find the rational numbers between them by observing their means. But the limitation of this method is every time we are getting 1 numbers only, and so it is little complicated. So, we have to find out some method which helps us to find the rational numbers very easily. Now, we are going to discuss the method 3, which gives that idea very easily. In method 3, the steps followed are as follows. We have to add numerators as it is, we have to add denominators as it is, such that whatever the number comes, this is always lies between the given two rational numbers. Are you surprised? Yes, this is always possible. Let us look at this by taking one example. For example, consider two rational numbers 123 divided by 386 and 432 divided by 772. Then by adding numerator and denominator, we get 123 plus 432 is equal to 555. 386 plus 772 is equal to 1158. We get 555 divided by 1158 such that 123 divided by 386 is less than 555 divided by 1158, which is less than 432 divided by 772. In general, if a by b and c by d are two rational numbers such that a by b is less than c by d, then a plus c by b plus d is such that a by b is less than a plus c by b plus d, which is less than c by d. In this way, the numerators and denominators, we can see that the resultant number is always lies between the given two rational numbers. This method is helpful when the given numbers are very big and very easily we can find the answer for that. So, let us recall what are the things we discussed in today's class. First, we define what are rational numbers. Second, we observe what are the different properties of rational numbers like commutative property, closure law, associative property, identity property, inverse law and distributive property. Finally, we saw that between two rational numbers we can find many rational numbers exist. Hope you enjoyed this class. Have a nice day. Thank you.